Even if you're running the same model, the different ways that you deploy that model affect its performance. And there are different trade-offs to each way to deploy a model, which is what we're going to discuss in this video. The first option is APIs. This is just where you use the model like a Cloud API, an OpenAI API. You send a prompt and you get a response, and you pay based on the amount of tokens that you take up. But you don't have to manage any infrastructure, and you don't have to think about GPU processing because the model just works. But the trade-off is you don't have a lot of control over the model because the data is also going to someone else's server too, so your data could obviously be leaked. And you're dependent on their pricing, the times that they're up, and the different model versions that they use. And if the model version changes, then you have to adapt to that. Option 2 is cloud infrastructure. You can use an open source model where you can download the model like Llama or Mistral, and you can deploy it on a hyperscaler like AWS, Azure, or Google Cloud yourself. You'd be renting the GPUs and running the model on your own terms. But the trade-off is that there's more work to set up. But you can control the model a lot more, and you can configure it, and the data stays in your cloud account. Tools like vLLM and Kubernetes make this manageable, and we'll talk about those in a minute. Option 3 is on-premise. You buy your own GPUs in your own building. NVIDIA sells GPUs exactly for this. But this is mostly for bigger companies, and the normal person can't really afford them. They're used by industries like those in healthcare, finance, defense, because that data cannot be leaked and it cannot leave the facilities. So if you're using a hyperscaler, this data is technically still not within your facilities. It's expensive and complex, but you have total control, even more than if you just do cloud infrastructure. Option 4 is on-device. The model will run on a phone or a laptop, and it doesn't need internet to work, it doesn't need a server, it doesn't need API calls. For example, Apple Intelligence, if you have an iPhone, Apple Intelligence runs on-device. And you don't need internet to power this. And on your laptop, you can run small open source models with a tool called Ollama. It's completely private and completely free. But of course, you can only do this with small models because there's not a lot of processing power on these devices, and they're nothing compared to GPUs. But if you're using something small, you don't need any internet, and you can do on-device. Let's talk about running AI on your own machine, because you can right now for free, and you don't have to use an API. The most powerful tool to do this is Ollama. This is the one to start with because it's free, open source, and works on Macs, Windows, and Linux. All you have to do is open your terminal and type Ollama run Llama 3. Llama 3 is just a model that I can use as an example, but you can technically use any model you would like as long as you look into their website and see what models they offer. And then in a few minutes, you can chat with a large language model running completely on your own hardware. You don't need an API key, you don't need any internet, and there's no data that's leaving your computer. It's kind of like having a private ChatGPT that lives on your computer. The models are smaller than Claude or GPT, so they're not as quality as those models, but for small tasks like brainstorming, or if you want some coding assistance, or if you need something where you need privacy, it's incredible because it's free as compared to Claude and GPT where you have to pay a lot to get quality. Let me show you an example of running a model on Ollama. Let's run a model with Ollama. So first you have to download it, but all I have to do is type in Ollama here. And as you can see, there's a lot of things you can do. You can launch Cloud Code, you can launch Codex, you can launch a few things, but let's just do chat with model. And then you can pick a small model. One example of a small model is Gemma 4. And then all I have to do is click yes, and now it's downloading it. All I have to do is wait for the model to download. After about 4 minutes, the model finally downloaded. So now let me ask it a question. What is the capital of France? And it answers Paris. And this is all on my computer. All I have to do is download it. Of course, I just ran that on my terminal, but if you're not a big fan of terminals, you can always use LM Studio, which is the same thing, just with a user interface, a UI, instead of a terminal. And that's best for non-developers if you want to test stuff out. But as you can see, Ollama was pretty simple to use in the terminal. It was pretty user-friendly. So these small models that are probably around 4 to 8 billion parameters, which is not very big for an AI model, they're simple to run on computers, and it doesn't need much computational power to run one user's request, especially with its size being so small. But imagine you have an application and there's 1,000 users sending you a request. Your computer is not going to be able to handle that, even if you do use a small model that can run things pretty fast. There's no way your computer can handle 1,000 requests at once, which is why you need to start doing inference server deployment instead of this regular local deployment. Now, instead of using something like Ollama, you would need to use an inference server. An inference server is a specialized software that sits in between the users and the model. It handles the requests that are being sent, it manages GPU memory, and it batches when it gets multiple requests. It batches them together in order to get the results as fast as possible. One example of an inference server is vLLM, which is a pretty default choice for a lot of teams. It's open source, it gives you high throughput, and it uses a technique called page attention, which is just a way it uses and manages the GPU's memory in order to get the fastest results. There's also TGI, Text Generation Interface, from Hugging Face. Remember Hugging Face from our MTEB rankings? Hugging Face is pretty popular. And if your model came from Hugging Face, which is pretty likely, TGI is the path with the least resistance because it's easy to set up and integrates with the Hugging Face ecosystem. There's also NVIDIA Triton. This is usually used by bigger companies because it's an enterprise-grade serving platform, but it can handle multiple models simultaneously, not just one, and it supports every framework. And it's mostly built for companies that need reliability at a very large scale, and this is probably the most complex to set up. There's also TensorRT LLM, which is also NVIDIA, like Triton server, but this one isn't a server. It's an optimization toolkit. What does this mean? It just takes your model and compiles it into a GPU-specific optimized version. Based on the hardware that you're running, it's just able to make optimizations so you can get faster inference at a low latency. And it's usually used with the combination of NVIDIA Triton because it's compatible. But this one isn't a server. Just so you know, it works to just make NVIDIA Triton run faster. Keep this in mind. When I was running Ollama locally on my computer, that is not an inference server because it's not able to handle many user requests. It's just local on my computer and I can run it for myself. But these inference servers give us a step up so that we can create real AI applications, which is why it's so important to scale AI. If you want to scale it into a real app, it's take into account the infrastructure and the inference servers that you build. So the main goal of using inference servers is to get your responses as fast as possible. And inference server optimization, which we'll talk more about in part 5, the goal is to make AI faster. But how do you actually measure how fast AI is? Well, first there's times to first tokens, which is how long it takes for the AI to generate the first word. Because if your time to first tokens is too long, that means that the setup process that you're doing is taking too long, and then the user will get bored and not want to wait for a response. Next is tokens per second. Once a response is streaming, how fast do new words appear? Below 15 tokens feels kind of sluggish, and it's kind of like watching someone type really slowly. You do not want to have it that slow. You need it to be a lot faster, because the faster the responses are, the user will be more satisfied. Next is throughput. It's the total tokens per second it takes across all users in the system. So let's say your server can handle 5,000 tokens per second. And each response that the user gets is about 200 tokens. You divide that, that's about 25 concurrent users that can get fast responses. So the more throughput that your server can handle, the more users that it can handle. But if the responses are really long, it handles less users. But that number helps you determine how many GPUs you're going to need to build your app. So you would have to estimate the amount of users, and as the user base grows, you'll need more GPUs. What's one way you can improve throughput? That's batching. Batching is when you group a lot of users and requests and you process them together instead of processing them one by one. And this improves throughput dramatically because your server can handle more users. But each individual user might have to wait slightly longer because a request is bundled with a bunch of others. And that means that the latency is going to be high. And the latency is the amount of time it takes for the user to get their response. If the latency is high, then the user is going to get bored waiting around for an answer, which is why we strive for low latency. But when we do batching and improve our throughput, that makes our latency worse. So a lot of problems that come with production is how much latency can each user tolerate so that the server can handle more users. Because when you do batching, you can handle more users, which makes your app more effective and it can reach more people. But to what extent will these users wait for an answer? So you should measure before you optimize your inference servers, because without optimizing your inference servers, you'll have this problem of either latency or throughput, which is why in section 5 we'll cover how to optimize it after one of them is too slow or maybe throughput is too low, how we can optimize it so we can keep both at a steady level. So those are the different ways you can deploy your models. You can use APIs, you can self-host them on your own computer, or you can create inference servers where you could deploy them to other users in a real app. And you should measure your latency, your tokens per second, your throughput, and things like that, so you know what weaknesses your inference server has. And then once you get to week 5, you'll learn how to optimize your inference servers. The next video, we're going to cover the last lecture of week 4, which is Kubernetes and scaling AI for workloads.